Welcome to Electronics Classroom Series. I am Daniyal Qureshi, back after long, not in Wardha anymore. I'm in Ottawa. For those who don't know, I actually made a video last time, and you can go and check if you want to also know the story. Anyways, we will pick up from where we dropped off last time, that is electrical power. Okay, so here I don't have my favorite whiteboard anymore, but I do have this Microsoft Surface. This will be the new method that we will try, and please let me know how it goes. Without any further ado, let's get straight into our topic. Electrical power can be real or imaginary. Real power makes sense, but what about the imaginary power? If it is termed as fictitious or imaginary power, then why is it even considered? Well, get ready because today I will clear everything about electrical power. So make sure that you watch till the end. Okay, so first let's see the types of electrical power, and let's first have a snapshot. Everything in brief. So there are basically two main kinds of electrical power. First, we have the real, that's measured in watts. The other one is imaginary, that's measured in volt ampere reactive, VA. And alternative names for the real power is true or active power. In the case of imaginary, we also say it as reactive power. And real power is absorbed by resistive components or like resistive load. So resistor. And then in imaginary, we have reactive components that contribute this. Reactive components like capacitor and inductor, right? We have these two reactive components. And then when you combine them together, you get complex, you get the complex power and apparent power. Now they are essentially similar, but there is a small difference between them, that the complex power is basically a vector, and then if you take the magnitude of complex power, then you will get a scalar. But mostly we like in electrical engineering, we use the apparent power, and complex power is just like a complex number representation. So anyways, this is the basic snapshot of the electrical power, and we are going to see each of them in depth. And there is one more thing, the unit for complex power is volt amperes. Okay, so the first one is real power. So this is the power which most of us are familiar with. The real power is the actual power dissipated or consumed, essentially the same thing, by an electrical load. But the thing here is that the real power actually corresponds to the resistive losses. Resistive losses, by that I mean ohmic losses, like the heating losses, right? Heating loss. So if you just have a resistor, so it will consume the real power, okay? And the heating is actually something real, right? So that's the real thing. And then according to the equations, you have power equal to I square R, current squared, that's in DC. And also for the AC, you have the same current, but it's RMS, root mean square, right? That is what you use for the AC. And if you go further, power can also be written in terms of voltage and current. So it's VI rather than just current and resistance. This is in DC. And then the average, the RMS. This is for the AC, because in AC, you have to consider the RMS. Okay. And also the angle between the voltage and current. This is the cosine of the angle between the voltage and current, which will give you the average power in the case of AC circuit. But this is actually the generic equation for the average power in the AC. And if you have purely resistive load, then this component, like cos theta V minus theta I, the angle between voltage and current, will be 0. So this will be cos 0 is 1, and then you'll just have, power average equal to vrms into irms. This is when your load is purely resistive, and that is what corresponds to real power, also AC. And there is one more thing to notice is that we have instantaneous and average power. So here you see this is the average power, and this is if there is no denotion. So mostly it's like the instantaneous power. Here you see, like it's just the instantaneous current into resistance. So you'll have instantaneous power. But in the case of AC, you can also have instantaneous power, but mostly we have average power. That's what actually matters to us. So in this case, this is also average. Okay. If you want an instantaneous, so you'll not take the RMS of the current, but you'll just take the instantaneous value of the current. So if this is like instantaneous for DC, this is the same case. Like if this is the instantaneous for DC, can also be instantaneous power for AC. Okay, but we do not use instantaneous power for AC because it has no sense, because AC is always flipping positive and negative. So the average will be zero if you do it this way. But if you still want to calculate instantaneous power in AC, you can definitely do that using the same equation as with the DC. Okay, so second one is the imaginary power. Now, imaginary power is a bit difficult to understand, but here we go. In simple terms, the power used by reactive elements, okay, the reactive elements such as energy storing elements, capacitors and inductors is known as imaginary power. But the question arises why this is called imaginary, right? So see, reactive or passive devices such as capacitors and inductors, these devices, they do not actually dissipate power, but in turn they only act as energy reservoirs by sinking and sourcing energy. you know they let the energy they let the energy go in and out. Okay, so in simple terms we can say what it means is oscillate. And by the way, if you don't know this sinking and sourcing of energy in capacitors and inductors, I have made a really good video in depth about capacitors and inductors. Definitely go and check that out. Okay, so here is the simple explanation. So we have a capacitor, and you charge it in one direction, so the charge builds up. Okay, so if this is positive, and then once it is charged, you can also discharge it. So it will hold the electric field in one direction in one cycle and in opposite direction in the other cycle, right? And same is the case with inductor. So when you have positive cycle of the AC, the inductor will have a magnetic field in certain direction, whatever the direction may be. I'm just drawing this. And you can also have the magnetic field in opposite direction if you have, like, during the negative cycle when you're powering the inductor in opposite polarity, so you'll have magnetic field in opposite direction. So you see that overall, like, in a cycle of AC, the net energy used per cycle, so it will be just magnitude of energy released minus energy stored. During one cycle, it actually charges it up, and then during the negative cycle, it actually discharges it. So essentially, you see that whatever energy goes into these elements, it is also given back to the circuit, the same amount, the exact same amount. So this means that, like, the energy that is used up per cycle will be zero. So the real component will be zero, because there is, if just considering if these are ideal components, there is no resistance, assuming that, so they will not dissipate any heat, and they'll just oscillate, with the alternating current. Of course, we have to ignore the parasitic losses, can be resistive and capacitive. Just if we ignore that, so it means that these components will not use any real power. By the way, if you don't know about parasitics, you can always check my older series video on the parasitic elements. But you see, if we look within the cycle, we see an actual flow of current. So let's say if like we are in the positive cycle, you see that you have actual current flowing through the circuit, right? So the current is flowing through the circuit. Same is the case with inductor. It is other thing that this current, like over a cycle, if you see, we have positive and negative current, but at a moment in time, you see there is some current flowing through. So what this means is that this current that flows instantaneously actually takes up the capacity of the transmission line, right? So even though it's momentary, but still this thing, this reactive current, like reactive current associated with the reactive power is taking up the capacity of the transmission line, which is oscillating back and forth. So still we are actually using up the current carrying capacity that is specified for a conductor, or like transmission line, capacity of a transmission line, even if the result is like net result is no energy being used up, but still you see that the current is flowing, and hence it's very important, yeah, while designing the electrical transmission lines and power systems, that you take this into account. Because if these components are really big, so imagine if you have small capacitor, that's not a big deal. But if you have a large capacitor bank, or maybe let's say if you have very big inductive load, let's say you have a bunch of motors running, they can have this instantaneous like current that can flow in the circuit, because they will use this reactive power, and then this instantaneous current will flow through the transmission line, and this can reduce the real current component carrying capacity of the line, because that is where you actually use the energy, right? You don't just want this energy to be used in a reactive way, or something that is not producing any result, as you see that the real power is zero. So that is why, even though this is called as imaginary, but still it has real effects, right? But still we say that it is imaginary power or reactive power, which is oscillating back and forth. We do need it. There is actually need of reactive power, and it is used in generation of energy fields. It's important, even though it's oscillating back and forth and not actually using up the energy, but the energy fields, like the electric or magnetic fields, which are essential, and which also answers the energy storage. So these things, they are needed. So Q is how we represent reactive power, and the current squared into X, that is nothing but the reactance of the components. It can be capacitive reactance, it can be inductive reactance, depending upon the component, right? So these two are essentially, similar to the concept of resistance, but it is offered by these reactive components. And also instantaneous values of voltage and current. If you multiply them, you'll get the same, the reactive power. And for the average, again, if we go, it's RMS, because you need to consider root mean square for average power. And then now this time is not cos, it's actually sine of the angle between the voltage and current. So you see, higher this angle, higher will be your Q, right? So higher the difference between the voltage and current, or this difference, higher will be the Q, higher will be the reactive power. So this means that you should have as low of an angle between voltage and current, so that you don't use or like consume that much reactive power. And this is true, like this is the same with the power factor. So if the gap is less, the better will be your power factor, closer to 1, and that is how how efficiently you use the energy. So this average reactive power will be positive for inductor and negative for a capacitor. And why this is so? Because it's essentially by the nature of this component. So in the case of capacitor, you see that the voltage actually lacks the current waveform. So here you will have this this angle will be negative, and sine of negative angle will be negative. So that's why in the capacitor you have negative, right? Negative reactive power. And in the case of inductor, that's exactly opposite. So that's why you have positive, because there the current actually lags in comparison to voltage. So about the practical application, we already saw that it is used to make the energy fields, but these energy fields, the electromagnetic fields, necessary for the functions for the operation of inductive loads. For example, can be a relay, can be motor, transformers, and generators. Another interesting application of this is regulation of voltage levels. This is done by capacitive reactance. If you know about capacitive banks or capacitor banks, they are not only used to make your or correct your power factor, make it better, but they also stabilize the voltage on the line. This is because they also kind of store the energy in form of electric field. Now coming to our third point, that's complex and apparent power. So one thing we need to understand is that in real life, the components are not purely resistive. They will not be like, purely resistive, purely capacitive, or purely inductive, right? But they're often a combination of all these, right? So they're a combination of all these, like some complex combination of these, and will also contain some parasitic behavior. Okay, so you'll have this complex load. We cannot just use real or just imaginary. We cannot just represent the power used by them in terms of these real or reactive terms, but they will consume real as well as imaginary, like both of them in proportions that is according to the load. Okay, so complex power includes both real and imaginary components, right? So if we see, the complex power is made up of real, as we saw in the snapshot as well, right? Real plus imaginary components. Hence, it is a generalized representation of power applicable to any kind of load, right? Pure or combination. This not only the complex load, but this can also be pure, and I'll show you why. Because this is just a generalization. If something is pure, the other component will simply be zero, but you will still be able to represent it in terms of complex power, right? So it's just the case of how you represent. So the complex power mathematical equation is P plus JQ. So P is our real power and Q is the imaginary power, right? And then if we substitute, that is VI cos phi plus J VI sin phi. Now, please understand that these are the RMS values, the voltage and current. In this, they are RMS value. This is the basic equation of complex power. But for calculation purposes, we only consider. So for calculation, we only consider the magnitude. Okay, the magnitude or the absolute value, we can say, of this complex power. So if you do some math, and this will be the average. Okay, so magnitude of S average, you'll see that it will be VRMS into IRMS. Very simple, because we'll see in the relation how it's done, but it's very simple. So I squared RMS into Z. There is another way in which we can represent using I square RMS into Z. Now Z, this is essentially one of the first equations that we saw, but the Z here is total impedance of the circuit, right? It represents the total impedance of the circuit. So whatever you may have, like the load can be complex, but this represents the total impedance of the circuit, right? And this means that the complex power, magnitude of complex power, is nothing but apparent power. So this is how they are connected, how they are same, like similar. Now complex power, you can say complex or apparent, is the actual power. Okay, is the actual power which the source experiences. Okay, which the source experiences. And by this, what I mean, it literally means, literally what it means is the voltage across the source, or across the line, and the current flowing through it, like considering these two, current flowing through it, like the basic equation of power. The only thing that's different here, if we consider just a resistor, but here it's a complex load. Okay, so it's like can be a combination of capacitor, resistor, or inductor. But still, at the end of the day, you are just concerned about these two things: the voltage across and the current. This is what complex and apparent power represents. So coming back to the pure one. So from this equation, you see real plus j. That's the imaginary component jq. So here you see, if let's say if your component is purely resistive, so in that case you'll just see that you have some value for p, and there will be no component for this term like jq, because the resistor only dissipates real power, so you will not have the imaginary term. But in the case of, let's say, a pure capacitor, then in that case you'll not have this real value. You'll just have this imaginary term, and same is the case with the inductor. But the only difference between capacitor and inductor will be the difference in their signs, okay, their polarity. So one will be positive and other will be negative, just that, but they will not have the real component. But again, in the real world, as we have parasitics, even these components, the capacitor and inductor, they will have some parasitic elements inside them, like resistance and like parasitic capacitance and inductance, whatever. So even these things, they might look pure to you, but then you'll have some real value to them as well. And finally, we'll see the phasor relationship between all these. So we have this phasor triangle QP, and this is phi. This is our real, imaginary, and this is the parent. So this is how they have relation. And according to simple trigonometry, the phi, you already know, is the angle between voltage and current. Okay, and p here, according to simple trigonometry, will be as cos phi, and q, real will be as cos phi, and imaginary will be as sine phi. That's simple. And what does this mean? For more intuition, this real component will be just like a real component of S or the apparent power, simply. And the imaginary or reactive will be the imaginary component of the S. And our S is nothing but, a complex number. That's why we can have real and imaginary part. And then finally, the thing that we care about is the magnitude of this thing. So according to simple trigonometry, you see, will be root of p square plus q square. And if you substitute the values for p and q, you will get the same result, that is vrms into irms. And this thing is nothing but the apparent power. One last discussion on this topic is the lengths of the vectors. Assume that we have similar s, but here the angle is higher, okay, the phi is higher, and in other case the angle is lower. And I will continue to draw other components. So this is the p and this is the q. In this case, this is the q and this is the p. This is our s again, and phi. So here you see the p by q is less, right? And here the p by q is more. Why? Because the numerator in this case is smaller and the denominator is bigger, and opposite is here. So the first case where we have p by q really less, so this means that we're using more reactive power than active power. Okay, and this is not good, because real power is the main thing, and if you are using it, then it is good. But if you are using more reactive power than that, then it's bad. So the other case will be naturally more suitable, because we are using more real power as compared to reactive power. So this is what we generally see, and this is why we also correct the power factor in the electrical circuits. This just means that we are using our power efficiently and not wasting our channel capacity for just the oscillations by the reactive components. I hope that you enjoyed the lecture, and if you did, then please like, share, and subscribe. Also, comment down below if you have any questions or queries and about this new method of delivery, if it is good or not. Thanks for watching, and see you there.